So I constantly get my skepticism reinforced when I look at climate change and climate science. And sometimes it's because it's shitty methodology in a paper. Sometimes it's because I see values that are presented without the entire range of uncertainty, and sometimes the range of uncertainty is the exact same magnitude or on the same order of magnitude as the value that's being presented. And in a lot of cases, it's always the damn value, or most cases, it's always the damn value that would give the worst case scenario result. The other thing that I see is a lot of claims of precision, which are just not valid. And one of those is this here, this NASA press release. And it says, globally average temperatures in 2015 shattered the previous mark set in 2014 by 0.23 degrees Fahrenheit, 0.13 Celsius. Only once before, in 1998, has the new record been greater than the old record by this much. Wow. Way to go, NASA. You managed to successfully account for the variation and change in temperature on our daily cycle, on our yearly cycle as our planet orbits elliptically around the sun, and for the variation between the poles and the equator. Way to fucking go! Good job, guys! You are fantastic. And not only did you do that, you did that to 0.13 degrees Celsius. Right here, it says that, 0.13. So not only is it a tenth of a degree Celsius, you actually can measure it to the hundredths of degrees Celsius. And that's what this says, right? There's no plus or minus values. There's no standard deviation. The claim is being made that they have the ability to measure with precision to 0.13 degrees Celsius. Forgive me if I don't believe you. Right, and I wanted to sit there and do this presentation because I was shocked when I saw this. Absolutely shocked. Doing it a half-assed, lazy way. I wanted to find the number of stations. I wanted to take into account the difference in maximum and minimum temperatures of the Earth. And then I wanted to turn around and look at like standard deviation and come up with something there. And I even found a National Institutes of Health article that told me a way that I could average, or that I could represent the actual variance and standard deviation of a population just with the maximum and the minimum values and the number of stations. But I couldn't find the number of stations, and I couldn't find the standard deviation, and I couldn't find the variance, and I couldn't find the actual values that I needed for this whole entire endeavor. So I decided I had to go look at the data, and I did. There are three major data sets that are curated by NOAA, NASA, and the UK. NOAA's MLOST is a combination of the ERSST, which is the sea surface temperature reconstruction, and the land surface temperature data set that they use is the GHCN monthly database. NASA's GISTEMP uses GHCN again and the ERSST again, but they also add in the SCAR for Arctic stations. And the UK Met Office uses CrewTemp4 and Hadley SST, which is their own brand of stuff. But when you go look up CrewTemp4, they use the USHCN series. So basically, the GHCN, the USHCN, very, very, they have more stations in the GHCN. But when you look at all this stuff, it's probably the same exact data set. And then when we look at their sea surface temperature data set, it all comes from this ICOADS data set. And we go look at NOAA, and their ERSST is determined by ICOADS. So pretty much no matter which of the three groups that you're looking at basically the exact same data set. It's not independent of one another. It's all in how they prepare it and how they look at it. And in doing that, I was definitely going to have to go find the GHCN. But I was evaluating the ERSST, which is based off of ICOADS, and I tried to find ICOADS, but ICOADS is reported in ASCII, and I didn't want to have to code to interpret the ASCII file. And I didn't want to use the ERSSTs because that's not dailies, which I'll go into in a moment. And I also had this concern because the ERSST has its missing data filled in with statistical methods. And if you're using a statistical method to infill your data, you cannot use a statistical method to validate that data. It would become self-referential in a circular argument. I mean, it's just going to look better than it is. So I eschewed the ERSST, not because of being ultimately lazy or that there's some sort of evil conspiracy or I'm trying to do that. It's just, it's a pain in the ass, and they also do some funky things there. So when I go and take a look at the GHCN monthly, what they do is they compute simple averages based on the daily observations of meteorological elements, which for temperature is the maximum and the minimum temperature. Bit of a concern there If we're all using the GHCN monthly and we're producing yearly averages and we're averaging months, then we get into a question about averaging averages. And when you average averages, that's not very good, unless the population means are the same. But the truth is that I don't expect our monthly means to be the same. I don't expect the global average temperature of January to be the same as the global average temperature of July. I just don't expect that. As such, I would not and do not believe we should be averaging on a yearly basis and for yearly comparison, which is what we were talking about here, be doing monthly temperatures. I think that you're going to be dealing with a loss of data. And there's actually a couple different things that you can look at. One is Simpson's paradox, if you want to look at this a little bit further. And this gentleman actually did a fantastic little blog entry with some of the problems of averaging averages, where what values do you use and how do you use rational subgrouping. So rational subgrouping, in my opinion, and this is my opinion, should be all of the stations, all of the data, all of that for 1 year. And that is what the methodology kind of calls out for, and that is not what they're doing. So that's kind of a concern of mine, and it's a concern because you're going to lose information on that data. So when we go to take a look at the GHCN daily, it mentions that it has 90,000 land-based stations. Wow, that looks fantastic, right? Except it also mentions 2/3 of which are for precipitation measurement only. And that does not mean that the rest are all for temperature measurement. It's actually include all this other crap as well. So really, like, I came to this point and I said, okay, well, there's no real way that I can get around not doing the data. So you can actually find their server and download the data. It's available. It's free. It's not encrypted. There's no hack or anything like that. And you can download this, which is what I did with the 2015 CSV file. It is 187 megs on the server. It is about 1.2 gigs when it's fully unpacked. And there's a README file associated with this, and I wanted to take a look at it, to look at the units that we're using, if we're talking Fahrenheit or Celsius, right? But when I came to read it, I found out that Tmax and Tmin is the maximum and minimum temperature in tenths of a degree Celsius. Holy shit. Just holy shit. We have claims of hundreds of degrees Celsius, but the maximum that you can actually get in the data set is tenths of a degree. Like, the reality is, and I understand this mistake, it is a common mistake, but you should not be making it. We are not measuring global average temperature. We are averaging global temperature measurements. Two distinct things. If you are measuring the exact same object, then you can use multiple measurements to get higher precision. You absolutely can do that. You cannot do that if you are not measuring the same object, which we are not. We do not expect Station A and Station B, separated around the fucking globe, to have the same global average mean. We don't expect that, and we shouldn't. So if they're averaging months, and if they're averaging months, which are averages of days, then you run into this problem where they're basically quashing your standard deviation, your variance in your data. It irks the crap out of me whenever I see this. Irks the crap out of me. So I downloaded the data and I ran it. I ran into some problems almost immediately when I started going into the CSV file. I tried to import the entire thing, which again, 1.2 gig file, into Excel. It doesn't work. Excel has a limit on the number of rows, which I didn't know because I've never played with a data set this big. At least not outside of controlled laboratory conditions with a whole bunch of other conjoiners. So I ended up having to try to bring it into Access, a 1.2 gig file. I ran into the fact that Access has a 2 gig limit. So I ended up splitting the file into 4 separate CSVs, delineated into groups of 10 million rows apiece. The CSV splitter created these 3 files. As you can see, they're all generally about the same size, with the exception of this one, which is just the remainder. These were then imported into Access databases, each one here, at which point the data was screened for temperature data only. So I extracted the temperature and the stations and the date, as date, stamp, stations, magnitude, type, etc. All right. Then from there, that was all dumped into, and all of those exported queries were brought into this table up here, which I'm not going to go into and try to load because it's rather extensive and there's no real point in looking at millions of temperature measurements. And then I QC'd the data, right? So we already discussed that a temperature measurement for the average is the number of stations averaged together with their Tmax and Tmin, which means 2 temperature measurements per day, 365 days, if a station is not outputting your basic QC, which is what we're considering our sample. If it's not fitting that description, it was excluded. And that left me with 4,500 stations. 4,500 stations. Just by sitting there and eliminating those that are not actually producing reliable temperature measurements. And from here, I went and got my mean and my standard deviation. And here it is. It's 11.4 with a standard deviation of, holy shit, 12.6. That's quite a bit of standard deviation, which, again, I wasn't entirely surprised by. I was actually very surprised initially and tried to double check all of the math, and that's what it comes out to be. But when we actually sit there and compare this to the number of samples that we would need to detect a 0.13 degrees temperature change in year on year, we need a total of 122,085 stations. This is using these statistics that are proportional to type 1 and type 2 errors for a 95% certainty. 95% confidence interval. In order to report what NASA reported, we need 0.13, or we need 122,000 stations. Holy fucking shit. We don't have anywhere near what we need to be doing or making those claims. So already, NASA has overstated its precision, not just in terms of what the instrumentation is capable of, but also in terms of what our actual stations are when we take into account all of the variants, which, again, they don't track in the method that they're using. If we were to talk about just the 0.4 degrees, which has supposedly occurred since about 1980, well, we can't detect that either. If we were to talk about 0.8 degrees rise, which is supposedly the entire curve, the entire trend, 0.8 degrees rise, we would be able to detect, assuming that all of the stations are randomly distributed. It's as long as it is a representative sample, or the stations are the stations and their actual samples are representatively distributed, we can do that, which they aren't. If we take a look at the 2015 data, it's North America over here is pretty well covered, but Australia isn't, and there's virtually nothing in Asia and Africa. If we go back to 1980, this is the distribution of 1980. I mean, the actual station distribution doesn't even look the same, much less that it's randomly distributed. And this is actually testable. There's a statistical test called a t-test that I performed on both sets of data for the latitude, and I put in the absolute values for the actual latitude data for the equator to the poles, and the result is that there's only a 3.7% chance that the means are the same. We don't have randomly distributed data. We don't necessarily have a representative sample. We don't have the ability to detect climate change. And given all the other issues that I've pointed out, how is this considered acceptable? I mean, even when we sit there and we start talking about QC, the effect that QCing the data has is rather significant. If we're going to sit there and say that 0.13 degrees Celsius is a significant factor, if I go in and I QC my data, I get 11.4 degrees C. If I just take strictly the temperature data of all of the stations, regardless of QC, it goes to 11.76. We're talking about almost 3 times the magnitude of the difference of what NASA is reporting just in the output we get as to whether we QC or don't QC the stations. When we go back to 1980, we have a different set of stations that are even operational or in our QC data set. We have a different distribution of the means. If you're telling me that you can somehow get 0.13 degrees of precision off of this, I'm not seeing it. I'm not going to buy that. And I don't think anybody else should either. So when I went to go sit there and find out how the fuck we were sitting there and coming to this 0.13 degrees, there has to be some sort of reasonable justification, I landed on this page. And what it says is GISTemp prefers to work with temperature anomalies, not absolute temperatures. Temperature anomalies are computed relative to the base period of 1951 to 1980. The reason to work with anomalies rather than absolute temperatures is that absolute temperature varies markedly in short distances. No shit. It varies markedly in short distances and over time and all of those other wonderful things. And while monthly or annual temperature anomalies are representative of a much larger region, yes and no. It doesn't matter if you do your anomaly calculation and it's representative of a much larger region. At the end of the day, if your data set is insufficient to provide your data, then your regions and your averaging and all the spatial weighting that you want to do with the world isn't going to change that. But they did reference this paper and said that temperature anomalies strongly correlate out to distances of the order of 1,000 kilometers. Strongly correlated. Strongly correlated. Wow, let's test that. All right, so you go to this paper. And it's a wonderful paper. NASA did I'm glad that they made it available. Hansen's a little bit crazy, but he actually is a pretty good scientist. I mean, he does present all of his logic and reasoning. Even if his fundamental mechanics are crap, he does present all of his logic and reasoning. And this was published in 1987. This describes how they do temperature anomalies. And I have issues with the paper. What a surprise, right? I have an issue with the paper. Error estimates are based in part on studies of how accurately the actual station distributions are able to reproduce temperature change in a global data set produced by a three-dimensional circulation model with realistic variability. So I'm supposed to believe that you have a GCM which is going to test the actual temperature distribution amongst different stations, assuming that, or knowing that you don't have the ability to actually detect any of that temperature across the stations which were used to build the climate model. Not buying that. And they even talk about it a little bit further down here in the same page and says, such global data would provide the most appropriate comparisons for global climate models and would enhance our ability to detect possible effects of global climate forcings. Great! So you are going to use a climate model to validate a data set which you are then going to use to validate a climate model. Nobody sees a problem with that. Nobody sees that as a circular argument but me. Oh, okay. And you go through the rest of this paper and you find some things that are, frankly, a little bit disturbing. It's like watching somebody on the cusp of self-awareness. And they see all of these reasons why they probably shouldn't be doing this, and they do it anyways and publish a paper on it. And that's how this reads the whole way through. I mean, you got this map here, which is all kinds of interesting. It's got the number up top as to when temperature recording began, and how many stations are there, right? Then we go into the discussion that they've decided that 1,200 kilometers, again, remember this, temperature anomalies are strongly correlated at a distance of 1,000. Well, they actually use is 1,200, and they say that the correlation coefficient falls to 0.5 at 1,200 kilometers. Well, let's rephrase that. It falls to 0.5 at middle and high latitudes in certain regions where we have lots of data, and 0.33 at low latitudes where we don't have very good coverage. So the 1,200 kilometer limit is not really entirely accurate. The idea that it's strongly correlated is not really accurate. Personally, I am not a big fan of seeing a correlation of 0.5. If you start coming to me with data that is correlated at 0.5, I'm going to tell you you're full of shit and go get me some more data. I generally don't consider a correlation to be a good fit unless it's 0.85 and above. But that's personal taste in mathematics. I guess physicists have lower standards than engineers do. And that's what we see. So they go into here and they even show that the actual distance away has a significant, there's a correlation between distance and correlation, if that makes any sense. And the closer you are, the more likely the temperature trend or change is accurately replicated by a station. Well, no shit. I mean, the closer you get to the two stations are, the more likely they're going to be representing the exact same physical phenomenon. That's not exactly a statement of magical awesomeness, but 1,200 kilometers is a bit much. And then when we start going into their actual method, they have this here. And it kind of concerns me. It looks like it's code. It does. It also looks like it is a really, really bad way to do things. They break all of those boxes up in the previous figure. You know, this one right here, down into 100 sub-boxes per here to try to get a roughly equal weighting average of temperature. And then they run this, where every single station that reports within 1,200 kilometers is put into a list of potential temperature stations, and then they run through, and then supposedly what they're trying to do is weight average the impact it has based on the distance away it is for the sub-box, and then they're going to take the sub-boxes and they average the sub-boxes together. They get the big boxes, which they average again to get the larger and larger boxes. So we run into the exact same problem that I mentioned about averaging your actual temperature data set on a monthly basis all the way through. Like, apparently this seems to be a generally accepted, let's just throw all of the guidance of statistics out the door and do whatever the fuck we want, and we'll put in whatever error estimate we want, and that's how we're going to compose ourselves. But if we actually go into the math here, it's a little bit disconcerting, because it looks like, and I'm hoping I'm wrong when I'm reading this, I really hope I'm wrong, that if you take your temperature differential here and you plug that in here, those would cancel, which means that it really looks like it resolves to something like this. And if we actually, if I'm reading this right, where these values are essentially updated for every single n, for every single iteration of this process, then that would mean that the actual resolution of your final temperature is equal to, or your supposed weight average temperature differential thingamabob is more accurately reflective of just the second to last temperature in your ordering sequence. And they did address this a little bit, that this might be sensitive to the number of temperature stations and the ranking order of those temperature stations. They do talk about that. They say, oh, well, you know, it had a substantially lower effect than what was had for the actual overall temperature trend. Well, no shit. If you are talking about 200 kilometer increments, that has a substantially greater impact on stations that are closer to those 200 kilometer increments than the stations that are farther away. That was demonstrated in your previous box. I mean, it doesn't mean that the order of the stations from farthest away to closest, or over time, or anything like that, is gonna really change things, right? If your statement is correct, that the global average temperature within 1,200 kilometers is accurate, and you're saying that it gets even better as you get smaller distances, at 200 kilometers, we should get very good similarities between what we have, regardless of the ordering of stations. That's what we should get. And when we're averaging the averaging, again, you're losing information every single time you do it. So I have an issue with the methodology. I have an issue with the fact that it's self-referential. But then we get into some of the other stuff down here, which, you know, you start seeing that there's moments where you go, how do you not see this is a problem? And one of those comes in with their qualitative argument that they say, oh, well, we compared a visual temperature map of our method versus the actual climate model they use. Now, again, I have an issue because it's a self-referential argument, but even if we use their statement, the climate model, which is the validation of this temperature averaging tool, shows more variation than the temperature monitoring tool. So this is not an accurate representation, regardless of whether you come at this from a statistical, mathematical point of view, or whether you come at it from a modeling average. It's not accurately depicting the range of variance that we should be seeing. And they do talk about that, and then they say that they really that while they believe they've come up with some sort of reason as to why they think that occurs, but then they also mention that the model in and of itself is not as variable as it should be. So if the model is showing more variability than your data, and the model is showing is not variable enough for all known natural phenomenon, and your data is suppressing, your data method is wrong. It's outright wrong. It's not demonstrating and behaving the way it's supposed to. That's kind of the end of the argument there, but what the fuck do I know? I just have to play with numbers for a living. And when you start coming down here, there's other moments too. There's other fantastic moments. I think it's actually a little bit further up here. where they talk about global average temperature and various ways in which this has, not necessarily this method, but other methods have been tested. And they found that when you use a GCM to estimate errors in meteorological variables due to spatial gaps, in a previous study, they found that the error was between 0.5 and 1 degrees Celsius. Again, not 0.13, 0.5 to 1, a whole degree based on this. For spatial averaging, their argument is that, well, that doesn't really apply because we're doing our shit over time. No, it still applies. If your uncertainty is plus or minus a degree, right, and you're doing it over time, your uncertainty year to year is still plus or minus a degree. Your uncertainty as displayed in your own methodology is not sufficient compared to its validation tool. It drives me up a wall. Then you sit there and you start going through this and you find out that what they finally decide to settle on is a 0.04 to 0.07 degrees, and that's what they use. That's how they decide it, that it looks like it's the standard deviation is 0.04 to 0.07 depending on where you are in the map. Great. Fantastic. But then they include this statement. The error bars when which we display in our figures are plus or minus 1.96 sigma, which is the 95% confidence interval, based on the GCM sigma. Although formally a 95% confidence limit, we only regard it as an approximate measure of uncertainty. No fucking shit you only regard it as an approximate measure of uncertainty. You violated nearly every single math rule. I feel like I'm getting math raped here. This is terrible. It's absolutely fucking terrible watching this. We are losing data and information. So then they do other things. They do try to control for other things using this data. They screen for population centers, so they decide to drop out anything with a population center, a city or a town or something like that with a population exceeding 100,000 people to account for the urban heat island effect. But that's a bad methodology too. I was raised for most of my life in Marblehead, which has a population of 20,000 people. It's also about 97% developed. I mean, you go to Salem, which was our next door city, and that was only 40-something thousand people. You go to Peabody, it's like 50. Revere is another 50. And this is what the map looks like. This is what the satellite coverage of this area looks like. It is nearly entirely developed. If this urban heat island effect is a thing which you identify in this paper, then the methodology that you're using to screen for it is inappropriate. It also means, and what that translates into is that really the actual urban heat island effect is probably significantly larger in the data set that they're using than what they're actually presenting. That's what that translates into. It just baffles me. I mean, they just apply whatever error they want. They use faulty methods. And they go about this. And this was in 1987. And we're still using, if not the same methodology, a similar methodology, as was described by NASA for NASA's data set, which NASA somehow got to 0.13, which, again, we cannot do. So I decided to sit there and look at this, right? Because I know temperature stations are expensive. And a standard size Stevenson screen is about 625 pounds, which translates to about $883 US. A GPS transmitter is somewhere between $25 and $150. Temperature probe, which we could even get more specific down to, say, thousands of degrees if we want to start reporting in hundreds, is somewhere between $20 and a couple $100. Plane flights from Boston to Hong Kong, which I figured those were the two most disparate locations around the world, are around $800. I know it'll load here and do its little funky thing. But at $800 for a round-trip ticket. And a solar panel is about $200. It's a little bit less than that. So I calculate that roughly a Stevenson screen bought with all retail materials, not bulk shipment or anything like that, not using U.S. buying power, just somebody going out and building one of these things, the actual cost would be about $2,000. I'm assuming that if we were to put somebody on this task of trying to build these stations, right, it would be about $1,000 for them to put one up a week on top of that, which would come to be about $3,000 for the entire complete project using essentially retail prices. But I'm assuming the government is incompetent, and as such, $3,000 won't cut it. We're just going to make it $10,000 or less. I think that can accurately represent the cost to distribute these stations across the globe, anywhere we want, right? And if we were to put down a million stations, again, we only need 122,000 stations to measure at 0.13 degrees, which is what we're claiming. But if we were to drop a million stations worldwide, and we were to just do this, just go through the process and set them up, we could have a temperature monitoring station network that we can turn around and make these claims with. Furthermore, we could also sit there and have our stations set up so rather than they're doing T-min and T-max, they have 24 hours or 24 data points instead of 2 per day. And then the 24 data points would be taken every hour. That would actually allow you to significantly decrease the natural variation. Because right now, if we were to say that the average daily variance or the deviation between the high and the low is 20 degrees, it means that we're already essentially at 10 degrees. If we map that entire thing, well, now we have a temperature record for a temperature point for each point of the day, and we can actually accurately say, well, the variance in the data is a lot less. So we wouldn't even need that many. But let's just say we put in a million. The cost would be about $10 billion, assuming $10,000 for your setup and a million stations worldwide. Way more than what we need. Just going over the top, 10 billion. That's a lot of money. But when we go to the Government Accountability Office, we find that we spent $11.6 billion on climate change, plus $26.1 billion based on the American Recovery and Reinvestment Act. We spent almost $40 billion on climate change, and we don't have the ability to detect it. This is offensive on so many levels, that we are spending money for a problem that we don't know exists. Had we started this project in 1987, we would have the ability to have monitored, and I couldn't make a claim or a comment on it. It costs a quarter of what we spend in a year to have an appropriate monitoring network, and we can absolutely turn around and make this way better than what we have now and interface with the data. And when we sit there and we take a look at the fact that we have more CO2 that we're putting in the atmosphere every year now than we did at the time of 1987, this is what we should have done. And we've been spending fairly consistently on it all throughout this time. If we turned around and ends at 1993, if we went back to, say, 1987 and we said, hey, our data is fucking shit, let's spend $1 billion a year on $1 billion a year on new stations, by the time we got to somewhere around here, we would have very good data. It wouldn't be perfect, but it'd be good, right? We'd have almost 20 years of data. Almost 20 damn years of data that was very good, high quality, high resolution data with high levels of precision that's randomly distributed. I don't understand what the problem is. I just don't get it. And when we sit there and we look back at all the things that I've talked about, right? I mentioned the distribution of the stations. I mentioned the shift in the mean of those stations in regards to latitude. I have mentioned the effect and the magnitude of the impact that QCing the data has on the data, which is greater than what we're reporting as our precision. I've talked about the limitations of our instrumentation to only be hitting 1/10 of a degree Celsius, even though it's being reported to the 100th of degrees Celsius. I have sat there and mentioned the problems that come in with averaging averages, and how they're not carrying their standard deviation through the actual whole process. I have mentioned the problems with the self-referential argument. I mentioned what could potentially be a fatally flawed math problem. I mentioned the point that there are other papers which indicate that the methods that they use to derive their error shows that it should be significantly larger. None of that somehow phases the whole entire reporting of this. It's still the global look at global climate change. It's significant. It's not. It's not statistically significant. The increase in the rate is not statistically significant. It's not going to be statistically significant. You can wave your fucking arms up in the air all you want. It's not going to change the fact that it is not significant. And I understand that there's a lot of people who won't get this, and there's a lot of people who are going to ignore kind of what I'm having to say or dispute it. The reality is that if you don't have data, your response is not to come up with a new mathematical solution to represent the data. Otherwise, we wouldn't have statistics, which is meant to describe data. We just wouldn't be using that. We'd just say, okay, well, we took a sample and here's how we math our way to the rest. We can't do that. When you overstate your precision, you're lying. In science, you're lying. It violates your ethics and the code of ethics that's supposed to run in all scientific organizations to oversell what your capabilities are. It is a problem when we start talking about politics and political decision-making when we don't even know that it exists. We can't show that it exists. We can't. And when we start talking about how we're accounting for various variables that we can demonstrate, I mean, even Hansen's paper demonstrates the effect of the urban heat island effect, even though he didn't screen his data appropriately for all of it. When we factor in all of this stuff, the problem isn't that I'm not sitting there and saying that CO2 isn't causing an effect. I'm not saying that CO2 can't cause an effect. I'm not saying there's a global conspiracy or whatever the fuck else that you want to throw at skeptics as something that they believe. I'm saying that it doesn't matter what is said about climate science and climate change. We cannot detect it. Therefore, every single study which is based on this assertion by the data, which is insufficient, is also insufficient. All of the assertions are not sufficient. They're deficient in the ability to actually detect any of this stuff. And that's how this cascades through. If you have a problem with your primary data set and you start using that data set or those claims of that data set for attribution all the way through, then guess what? All of that shit is crap. So everything that we are spending money on at this point, every single thing that we are spending money on that is not improving our measurement of global average temperature or our ability to measure global average temperature is wasted funds. So we are rather than taking $10 billion and having $30 billion for excess crap, we are wasting $40 billion a year. That's really what this comes down to. That is the consequence of bad science. And if it doesn't offend you, there's nothing I can say that'll change that. It just pisses me off.